Welcome back to Pointers, a C++ mini-series. Hi, I'm Ghost, and this is part 2 of the mini-series. If you missed out on the first video, I'm gonna leave a card above. Make sure you go and check that out before you continue in watching this video. In that video, I go over the concepts like stack and heap and raw pointers that you must understand before proceeding with this video. Because in this video, we will be implementing raw pointers in code, and I will be referring to concepts from the other video. So like I said, if you haven't watched that video already, the card will be above. Make sure to click on that, watch that first, and then come back to this video. Also, everything that we do here will be in a GitHub repository, and I'll leave that link in the description below. But let's not waste no time. There's a lot to get through, so let's begin. Okay, so here we are in VS Code. The first thing I want to go over is how this GitHub repository is going to be structured. So since this is part 2, I have a part 2 folder here labeled as raw pointers because that's what we're going to be going over. Part 1 doesn't exist because, like I said earlier, it's just a concepts video, so there was no code. In future videos, you'll see the part associated with that video as a folder here. But for right now, we're on part 2, so we'll open up this folder. Okay, so the first thing that we have here is our source folder. This has each individual program that we'll go over one at a time. Now, to build and run each individual program, I created this batch file along with a shell file if you're on Mac or Linux. It allows you to build with either G++ if you have that, and if you don't, it allows you to use CMake. So it will give you the option. It'll also give you the option of which program that you want to build. So to give you a quick example, I'm going to run the batch file because I'm on Windows. But also make sure you're in the correct directory, because when you first open up the terminal, you're going to be just in the main directory, which is the pointers dash series. So for instance, I'll show you. You'll be here in the main directory, and you need to change directories because this batch file and the shell file are both inside this folder here, the part 2 raw pointers. So you need to make sure you change directories. In this case, I'm on Windows, so I'll CD, and I'm gonna copy and paste this. And just like that, now we're in the correct directory. So now I can run the batch file test. So the first thing that you'll be prompted with is to select which file you want to compile. This list represents what we see here in this source folder. Number 7, you can just exit if you don't want to continue. So let's say I want to compile and run this first one here, which is the stack. You select number 1. Now at this point, you get to choose which build method you want to use. If you have G++, then you can just use that one, which will be a lot quicker. But if you don't and you want to just use CMake, then you can use option number 2. Let me know how that works for you, because I'm trying to find an easy way for beginners to be able to compile the code that I create in these tutorials and be able to run them a lot easier. I don't know if this is going to be the best way, but let me know what you think in the comments. Anyways, to keep it easy, I'm going to select G++ because I do have it installed. So as you see here, it compiled it, and then it lets you know that it's running it. And everything in between these dashes here is going to be the program, meaning everything that gets outputted to the console. So in this case, everything that you see here is a part of what's inside of this stack CVP file. And the last thing you see here, you just need to press enter to continue, and it just exits that script, and you're done. If anything is confusing with those scripts, please let me know in the comments, and I'll be more than happy to help you out. The first script that we're going to open is this I1 stack. All right, so the only library that we need is this IO stream, is because we're going to be printed to the console. Okay, so that's that. And then we have our main entry point here. Now, the very first thing that I declared was this integer here named x, which I initialized to 42. Now, if you could recall what the stack is, I went over in the previous video. Well, this variable here gets placed into the stack first. What we're going to be doing next here is creating a pointer for this variable, which exists on the stack. Now, I have a bunch of these comments, which can be pretty detailed, but it will help break down exactly what is going on. So I'm going to open them up and just read them out loud, but they will be included in the repository, so you can go at your own pace. So the first thing that we want to do is break down this statement here. So pointer for stack address. A pointer is created using the asterisk, which is what you see here, which is an operator. Now this operator is placed after the type to indicate that the variable being declared is a pointer, not a regular variable. I also went over this in the last video, but you can see the difference here. So this integer here is not a pointer, it is just an integer because there is no asterisk right here. This one here, when we are declaring it, there is an asterisk right here. So this isn't just a regular integer variable, it's a pointer variable of type integer. Okay, now since x, which is the variable up here, is an integer variable stored on the stack, we need a pointer of the same type to hold its memory address. Hence, we keep it the same type that our variable is up here. This is done by declaring an integer pointer using int asterisk, which I just showed you a little while ago. The asterisk signifies that the variable is a pointer to an integer, not an integer itself. The pointer variable in this case, PTR, which I decided to name it that, is assigned the memory address of X. To obtain this address, we use the ampersand operator, which looks like this. And you can see that right here. This operator is known as the address of operator and is a core part of the C++ language. It retrieves the memory address of a variable when placed before its name. Now you can see that clearly right here. We have our X variable from up here. We have the ampersand right in front of it. So what it's doing is that it runs that operation and it returns the address of this X variable, which is on the stack. So it's an address coming from the stack, and then it assigns that address to this pointer. Now remember, as I stated in the last video, pointers hold memory addresses as value. So for instance, if I try to remove this ampersand, we're gonna have an error, and you can see it right there. That is because a value of type int cannot be used to initialize an entity of type int asterisk, which is a pointer. A pointer variable expects a memory address as a value. So let's put the ampersand back for our address of operator and everything is fine. And this last part here, since X is stored on the stack, its address is retrieved and stored in pointer, or PTR is what I named it, allowing access to X indirectly through the pointer. The pointer now holds a reference to stack memory rather than an actual value. Now, something to note really quickly is that the pointer right here is also on the stack, much like this X variable up here. I went over this in the last video as a visualization, so I won't go over it here again, but just note that the pointer is also on the stack now. Now at this point here, all we're gonna do is use cout to print out the memory address, and we can easily do that by grabbing the variable PTR and just insert it. But what about if you want the value instead of the memory address? Well, that's what we go over at this line here. So how to access the data a pointer is pointing to. To access the values stored at the memory address a pointer holds, use the asterisk before the pointer's name. This is called dereferencing and allows the pointer to act as if it were the original variable. Now, for anybody who's completely new, that may be absolutely confusing because we used it up here when we were declaring a variable, and now we're using it again to do this thing called dereferencing. So unfortunately, there are a lot of different things in C++ that you use in a different context, and this is just one of those things where we'll use the same operator asterisk in a different context, and it does something slightly different than what it did before, in this case declaring a pointer. So if PTR holds the address of X, then this PTR with the asterisk in front of it retrieves or modifies the data stored at that memory location, and we'll go over the modify part in just a second. So now we're going to do another print, but this time instead of just doing PTR like we did up here, we're going to put an asterisk in front of it, which will dereference that pointer and access the actual value, which should be 42. So at this point, we'll see 42. To recap, the first thing we're going to see printed is the memory address, and then we're going to see the value 42 because that's what it is right here. Now to modify the value, it's simple. All you have to do is use the asterisk again in front of the variable name PTR and just assign it to whatever else you want. In this case, we assign it to 100. Now this last print here, I just wanted to prove that if you print out the X variable, which remember it's up here, instead of using the pointer and then dereferencing, that you will see 100. Now the point of the proof is to prove that the pointer doesn't hold some copy of this X variable up here. It points to that memory address of this X variable up here. So whatever you do via the pointer, in this case, that we were able to modify this X variable up here, but through the pointer, it affects that memory. So by printing this down here, we're not going to see 42. we're gonna see 100. Now I'll compile this in a second, but I just want to go over this last piece here, which is very, very important. So in the next script, we're gonna go over heap, which will go over the delete operator. But I wanted to go over this here really quickly, because if you were to use it here in this case, where I'm trying to free memory of this pointer, which isn't pointing to some memory in the heap, it is pointing to some memory in the stack, it'll create a problem. Never use delete with a pointer pointing to stack memory. The delete keyword should only be used with heap allocated memory, not stack memory. If a pointer holds the address of a stack variable, attempting to use delete on it will result in undefined behavior. This can lead to program crashes, memory corruption, or unpredictable behavior. Stack memory is automatically managed, so it does not need to be manually freed. So make sure if you ever do anything like this, where you declare a pointer and point it towards some memory on the stack, which this is on the stack because we didn't use the new keyword, which would have dynamically allocated the memory. If we later on take that pointer and try to free the memory like this, you'll have an issue. So please don't do that. Anyways, with that out the way, we are done. So let's just compile and test this out. So we're going to use that test script that I wrote. We're going to select number 1, which is the stack script that we just went over. And we're going to compile with G++ to make it easy. Okay, so the first thing that we see here is the memory address. Remember, that's this line right here. And we're printing the PTR itself and not dereferencing, because we're trying to print the value of that pointer rather than dereferencing and trying to get the memory. Now, this is the memory address that I have. You may see a different number. It could be different. It could be anywhere in the memory at any point whenever you run a program. So it's most likely going to be different than mine. The next thing that we see here is the value via the pointer variable, which should be 42. That's this line right here. And as you see, we did dereference. So that's why we were able to access this memory, which is 42. Okay, now the last thing that we see here is this modified value via the X variable, which should be 100. And that is because right here, we did modify it using the dereference and set that memory to 100. And then all we do is print out that X variable instead of using the pointer and dereferencing, because we just wanted to prove that we did update the actual memory of this variable here. And there is no like random copy that we updated. So that's what we see here. Okay, so we're done with the pointer for stack. Let's go to pointer for heap. Okay, so now we have our heap script open. Remember, it's inside of here, the source directory, and it's the second one. Anyways, the only library that we need once again is the IO stream. And then we have some function called myfunc, which we'll go over in step 3. Then we of course have our main entry. So the first step, which is the allocation. When allocating to heap, you must use the new keyword operator, which is this operator right here, placed before the type you wish to allocate, which is this type right here, because we're going to allocate an integer. So then below, we allocate an integer to the heap with a value of 50. And you can see that right here. The new keyword, once allocation is complete, will return the memory address, which we store in our pointer variable called PTR. So we can see all that right here. We have our new keyword operator, which will allocate the memory for us. And once it's done allocating on the heap, all it does is return that memory address, and then we easily just store it in our declared variable pointer right here, which is of type integer. So the next thing right here is that we just print that value, and we use the dereference again to make sure that we get the value and we're not printing the memory address. Now this step right here, I'll skip over it and come back to it. But for step 2, which is the allocation, using the delete keyword operator, we can free the memory in which the pointer PTR is pointing to. However, note, since we are at the end of the program, freeing the memory was not necessary, because all the memory will be freed by the operating system. Now, once again, referring back to the last video, part 1, I did go over this. Your operating system does have a memory manager, and for each program that runs, it has its own set of memory regions. So every single one of those regions gets free of its memory by your operating system. So in essence, in this particular case right here, since we are at the end of our program, it wasn't really necessary to free this memory, but we'll go over when it is necessary to free the memory and step number 3. Okay, so going back up to this function that I have up here, which is step number 3. Now for something like this, that could be a function that is deeper into the program and there is no sign of the program ending anytime soon. If you have something like this, which is this particular scope here, we have another allocation right here. And right here, we can just do some stuff, maybe run a loop, whatever, it doesn't matter. Let's say we just did a bunch of things in between, but once we're done, then we need to free the memory. That is because it will be lost on heap with no access, since pointer, this PTR, which is right here, is popped from this temporary stack frame. Now I am referring back to my previous video, and I'm gonna keep saying that because if you didn't watch it, cards up there, make sure you go ahead and watch it, because it will make sense at this point if you did watch it. But in essence, if you didn't watch it, as we go through each statement, we begin to execute, and this pointer will get pushed onto the stack while this part of it will be allocated to the heap, which is long-term memory. But once we get down here, if we didn't have this delete operator, what will happen is that this memory that was allocated on the heap will continue to exist outside of this scope. And since this pointer only belongs to the scope, once we reach the end here, that PTR gets popped from the scope and cleans up in memory and doesn't exist no more. So at this point, you have no way of accessing this memory that is currently existing on the heap, which in essence causes a memory leak, which I went over in the last video. So it is important that you do have this delete operator here to clean up that memory before leaving the scope and prevent a memory leak. But I'll go over that more in the next video, where I go over the common pitfalls and things like memory leak. Anyways, that's pretty much it for pointers for heap. The next script that we will go over will be pointers for functions. Actually, really quick, let me just compile and run this. Even though we're just printing once, I just want to prove that this does work. And when we dereference this pointer, we should see 50. Okay, so now we're selecting number 2 and we see heap value 50, so it is correct. Okay, so back in our source folder here, we open up the function. Okay, so this one has a little bit of more things going on. We have this say hello function, we have this greet English, greet Spanish, another say hello function, which is just an overload. And also we have this new memory region, which I didn't cover in my last video, so this is brand new information, but I feel it is important to understand where the memory of a function exists. So let's go over that really quickly. Okay, so in part 1, we didn't discuss this memory region to keep things simple, but now that we are dealing with function pointers, it's important to understand where functions exist in memory. So what is the code segment, which is the memory region aside from the stack and the heap? Well, it is a special memory region where a program's compiled machine code is stored. Unlike this stack, which handles function calls, and the heap, which manages dynamic memory, the code segment holds functions so they can be executed when they are called. So why does this matter? Well, when using a pointer to a function, you're storing its memory address. But where does this memory come from? So let's rule out the incorrect locations, starting with the heap. The heap is used for dynamically allocated objects using the new keyword, and it does not store functions. The stack is for temporary function calls, those stack frames which I referred to in the last video, but functions themselves are not stored here. So the correct answer is the code segment. Functions live in the code segment, which is the text segment, and function pointers hold addresses pointing to this region, which you'll see in a little bit when we go over the code below. When a function is called, its instructions are fetched from this memory region. The function stack frame, which will have the local variables, return addresses, is created on the stack. Once again, I go over it in the last video, but the actual function remains in code segment region. So how does the function execution work? When a function is called, the processor jumps to the function's address in the code segment. The function's execution starts from this address. The stack frame stores local variables, return values, and execution state. Once the function returns, the stack frame is popped, but the function itself always remains in code segment. And once again, a bit of this information like the stack frame and how it's popped once it returns out of that function is everything I went over in the last video. So make sure you go ahead and check that out. So the key takeaways: function pointers hold addresses of functions stored in the code segment. Functions themselves never exist in stack or heap. Function calls push execution state to the stack, but the function remains in the code segment. So that might have been a lot and possibly a little overwhelming, but just note that every program has a few different memory regions. We went over the stack, we went over the heap, and this is just one of those other regions which stores the machine code. But I felt it was important to go over this so that way you understand where it's coming from when we are referring to the function's memory address. Okay, so let's just close out of this. Let's go down to the main function and then we'll deal with how these other functions come into place. Okay, so the first thing that we see here is that we are declaring a pointer for this function, which is the say hello function up here. But immediately you'll notice that it does look a bit different. And that's comparing like this one over here where we just created a pointer like so. Well, that is because when declaring a function pointer, you must include the function signature. Since the return type is void, that is written first. And I'm referring to this function up here, of course, the return type is void. So that's what you see first right here is the void. Next, parentheses are wrapped around the identifier for the pointer variable, which is called the func PTR right here. And that indicates that it is a function pointer. The asterisk before the identifier specifies that it is a pointer. Now, of course, this portion right here should look familiar because that is what we've been using, just like how we did right here. That is just declaring that it is going to be a pointer variable. Okay, so finally, the parameter list is included just like a regular function declaration. Now I'm referring to this portion right here, which is the parameter list, but obviously it's empty because that is the function signature. It is empty. And then next we are using the assignment operator. So you can simply assign the function's name, which is to say hello. Now I want you to understand something really fast. In C++, a function name by itself is already a pointer to its memory address. So there is no need to use the ampersand, which is that operator, which is what we use right here when we needed to get the memory address of X. So you don't need to use that here because the name itself, say hello, which is the identifier for this function, is in fact a pointer itself. Now, technically I could include it and it would still work, but your compiler will see that and just omit it either way, and it'll just work regardless because say hello is in fact a pointer. So essentially you can think of it as this already being a pointer and we're just assigning that directly to another pointer, which is called func PTR. And I believe that's what I say here. Why not use an ampersand to explicitly get the function's address? That is because a function's name is already a pointer. Assigning it to another pointer variable simply creates an alias, meaning that the function now has two names, say hello, which is what we declared it with, and now func PTR, which is what we're creating right now. And that's what you see down here. We can now use this func PTR to call this function and it will run the logic inside of here, which is just going to print this. But we can still use the regular function name, which is say hello, and it will still call the same function. Essentially, both of these things mean the same thing as far as the memory address. They're both pointing to the same memory location in the code segment, which is where that function exists. Now for this next portion down here, I want to go over a better example for when it makes sense to use something like this. So the function pointer example callback mechanism. Function pointers allow you to store the address of a function in a variable, making it possible to pass functions as arguments to other functions. This is useful when you want to execute different functions dynamically without modifying the caller function. So what does this example do? We define two greeting functions, the greet English and the greet Spanish, which is those functions that we see up here. The say hello function takes a function pointer as an argument. Now that is that overload, which we see right here, which we'll get into in a little bit. This allows us to pass different greeting functions dynamically. So we'll be able to pass in the greet English or the greet Spanish, and it'll both work automatically, or I should say dynamically. Instead of calling functions directly, we use a function pointer. So why use function pointers here? The say hello function does not need to know which greeting to use. the function pointer allows us to change behavior dynamically. This is similar to how event handlers work in real applications. Okay, so to go over the implementation, we create another pointer called greet pointer, which is going to refer to this greet English function, which if we look up here is just going to say hello. Now remember, this function exists in the code segment, and when we get this pointer here, we're just referring to where in the code segment it exists, its associated memory address. Now we save that to this greet pointer variable here, so that way we can use that and pass that into the say hello function here, which is not going to refer to this say hello function here. Now, I don't know if you know about overloads and how they work, but to quickly give you a rundown, you can have two functions with the same name, but when you have different parameter lists, like in this case, this one has a parameter of this pointer here, and this one has no parameter, it creates essentially like a specialization, like a separate function which will exist in the code segment. That way, when you call the say hello function, but you do pass in a pointer, then you're referring to this function and not this function up here. So anyways, we pass in this greet pointer, which is currently pointing to this greet English function. We pass that into the say hello function, which all it's going to do is print out this universal greeting, and then it's going to call that function, because remember, we can do that with this pointer here. Now for the last two lines, all we do is take that greet pointer and reassign it to the greet Spanish function, which is this function here, which is going to print hola. We pass that pointer once again into that say hello function, and this time it will call that function instead of the English, because that's the whole point of this. It's a dynamic way to create a callback mechanism. I hope that makes sense, but if it doesn't, let me just run the code and then you can see for yourself. So what you should see in the last two prints is you will see the hello first, and then secondly, you will see the hola. Anyways, let's run it. So we're going to run number 3, which is our function one. Okay, so as you see, we did print this hello first, because that's what we set the pointer to, the English version. And then the second one we see is the hola, because that is what we reassign this pointer to. And then we simply just call to say hello again, which is our dynamic way of calling whatever version we need to call. And that's it. If you have any questions so far, please leave them in the comments. And if you enjoyed so far, let me know how I'm doing. If you haven't subscribed, please consider subscribing. We are going to continue on to the next parts of this series next week. So if you're interested in the series so far, then definitely consider subscribing, hitting that bell notification, and liking this video. Anyways, let's continue. Okay, so back into our source folder, we're gonna open up the array. Okay, so simple enough, we have our IO stream again, and then we have our main entry point. Opening this up, we can see that we create an array, and this is going to be allocated on the stack, because notice we're not using the new keyword. Let's open up this information tab. So the array named numbers, which is what we call it, exists on the stack. Since anything on the stack has a memory address, this means the array itself also has a memory address. Arrays are stored in contiguous memory, meaning that each element is placed directly next to each other in memory. This allows us to access elements sequentially using pointer arithmetic. So what I mean by that is visualize that you have this numbers array right here. This variable right here refers to the beginning element, which should be this right here, number 10. Visualize it that it's right here in the stack. Now for the next element, which is number 20, is literally right on top of it, because it is contiguous memory, and that goes on for 30, 40, and 50, and they just stack on top of each other. So since this numbers variable here refers to the first element, which is going to be 10, you can just easily increment to the next element and keep going. The name of the array numbers represents the memory address of its first element, as I stated. This means we can store that address in a pointer and then increment the pointer to move to the next element. also, as I stated. So as you see here, we create a pointer and we assign it to the numbers. Once again, you don't need this ampersand, much like in the function example I went over. That is because, as I said, numbers itself is already pointing to this memory address, which is the first element here. So we can just take that pointer and assign it to some other pointer here. And now you don't need to add these brackets here to the declaration. Okay, so moving on, we print the first element by using the dereference again, and that should print number 10, which we'll see in a second once I compile and run. But where it gets interesting is that I take this pointer and I increment, which will go from this 0 here to this element here, which should be number 20. So when we print again, we are gonna print the second element, once again dereferencing here. Let's just run it real quick so that way you can see that this first element will be 10 and the second element will be 20. Okay, so we're gonna select number 4, which is for the array. And as I said, 10 and 20, which should be the first element 10 and the second element 20. Now in this comment here, I do go over some other examples that I didn't implement, but I'm just going to go over them really quickly. So this first example here, you can use this to traverse an array with a pointer. So instead of using an index, a pointer can be incremented within the loop. So for instance, when you think about this for loop here, how you have your index here, instead of using it like we normally do, for instance, we have our numbers and then we use the I just like that. You can technically just do this, where in this case we print the value, but then after you print the value, then in this case we increment the pointer, which will go to the next one. But know this, that it is not safe, because if you go beyond the bounds, then it creates undefined behavior. So you do have to be careful when you're just incrementing just like this. Anyways, the next example that we have here is passing an array to a function. So since arrays decay into pointers when passed to a function should accept a pointer. An example here is that we have this function called print array, which accepts a pointer, which will be our array, and then just some size that we're going to pass in. And then we use that size to make sure that we stay within the array and this for loop. And then we just call the C out like this to print the value of each one. And in this case, I'm just using the regular way, the normal way that you've seen before. But the highlight here is that we are passing in this array by pointer. The next thing here is using pointer arithmetic to access elements. So instead of using this index notation like I talked about earlier, you can use something like this, where we increment the pointer inside of it, and then outside we just dereference. That way we are accessing that that value, and it looks something like this. We have our for loop here, so we take this numbers and we take our index and we add the index to the numbers, because remember, numbers represents that 0 and it will always represent that 0. So if we add index, which starts off as 0, it'll just be 0, which will be the first element. But then when index becomes 1, we add 1 to numbers, which is 0, then it becomes 1 and 2 and 3, and then on the outside we just dereference, which will get our value. So we will get it in order. Okay, next here we have working with multi-dimensional arrays. A pointer to an array can be used to access multi-dimensional arrays. So example here, we have a matrix which is shaped as 2, 3, and then we create this pointer here, which the very first part here is the pointer, and then just part here represents the second dimension, the inner part of the multi-dimensional array. So anyways, we have this pointer like that, and then when we are printing here, we can just use the pointer like this, and then we can just access this one here, number 2. And then lastly, we have dynamic arrays and heap allocation. So unlike stack arrays, heap arrays must be manually allocated and deallocated using the new and delete operators. And that's what we see right here. We see this pointer here for numbers equals, using a new keyword, which will dynamically allocate this array on the heap, return that memory address to this numbers. And then here we're just accessing each element and assigning it some value, and then we use the delete operator. But since it is an array, you do need to include these brackets, so that way the compiler understands that it's not just a single object, it is an array, which is primitive. So you do need to include that when dealing with arrays, so just remember that. But yes, this will free up the memory on the heap of this array. Okay, so then that's it, we're done with that. Let's go over the 2 examples that I have. And then we're pretty much going to wrap up this video. Okay, so back in the source folder, we're going to go to this NPC example and then finish off with the real world example. All right, let's first open up this information tab. So the following examples demonstrate different types of pointers that we went over, which is a stack, heap, function, and array. These examples are intended for learning purposes only and are not necessarily the best approach or a recommended way to use pointers in practical applications. I put this little disclaimer here because like the way I'm using it here is just like definitely don't use it like this in a real world situation. I just wanted to take everything that we just went over and put it all together in this cool little program which involves like an NPC character. Okay, so with that out the way, the first thing that we're going to go over really quickly is this character class. So let's open this up. We have two private members, which is going to be the character's name and then the character's level, because they will have like, it's like an RPG, I guess. They have some sort of level. And then we have our constructor, we have our destructor, we have two methods here, this attack and increase level, so that way we can increase this character's level. And then we just have two getters for the get level and then the get name. I can open these up and quickly go over some of them. So this just prints to the console that this character, which will be the name that you pass in, has entered the game. The destructor just does the opposite, lets you know that this character left the game. This attack method here just prints the name and lets us know that they attacked the enemy. This increase level here takes some integer called level coin and just adds it to its current level, which is going to be 1 by default. And just of course these getters here. Anyways, with that class out the way, let's close this up. We'll go over the level up function a little after. Let's open up the main entry point. Okay, so a quick rundown. As you see here, we're going to go over the stack pointer, which is what we went over first, the heap, the function pointer, then the array pointer, and then just finish off with a little cleanup. So the first thing I did here was declare a variable type integer called level coin and initialize it to 5, which you can think of it as some coin that the character picks up, and then when they pick it up, they take that number, which would be 5, and add it to their current level. But the highlighting part here is that we create a pointer for this level coin and we just assign it like we've seen before. And with this print here, we are dereferencing this pointer, which should show 5. Next, we have our heap pointer, where we dynamically allocate the object which we're using the character, and we just named it as hero. And we're going to pass in this string here, which we're just saying that this person is a warrior. So this should allocate the memory on the heap, return the memory address to this pointer here, which is going to be our pointer variable of type character. Now this next part here is something that I didn't cover and you may not be aware of, but it's called the arrow operator, which I'm referring to this arrow right here. So the arrow operator is used to access a member function or variable of an object through a pointer. Since hero is a pointer to a character object, using this hero like this with the arrow pointer here and the attack, which remember is a method of this class here, and we see that right there. So using it like this calls that attack function which exists inside that object which the pointer is pointing to. This is equivalent to using our dereferencer like this, which we could have done it this way. I mean, I can actually write it really quick. So these two things are the same exact thing, but this one looks a lot neater, so it's best to just use the arrow operator instead of dereferencing and then using the dot operator. But yeah, that's essentially what I go over here. The arrow operator provides a cleaner and more readable way to access members of a pointer to an object. Remember, pointers are not references and require dereferencing, so arrow operators do so in a clean way to access members of a class. So yeah, so that's all we're doing here. We're just calling this method by using the arrow operator rather than dereferencing and then using the dot operator. Really quick, as I was editing the video, I just wanted to add that this only pertains to class objects and not primitive objects like float, integers, or anything like that. So you use the arrow operator to access any class members like variables or functions. You wouldn't use it on an integer or float because those are primitive. Anyways, I just want to clarify that. Okay, so the next thing that we have here is our function pointer, where we create a pointer called level trigger. And remember, it must match the signature of the function that we are pointing to, which in this case is this level up function up here. So the return type is void, and we see that we write it as void. And then of course, this is just the declaration of the actual pointer itself. And then for the parameter list, we have a character pointer and then an integer pointer that we are passing in. So that is what we put here, and then just assign it to the level up, which remember is a pointer itself, and that it exists in the code segment region of memory. Okay, so then here we can just easily use that pointer, which is an alias to the actual function level up, and just call it like so. Would have been the same thing if I just took this and replace it like that. It's the same exact thing. They both point to the same function. But in this case, we just created this pointer and did it like so. The next thing that we have here is our array pointer, which is allocated to the heap. And you can see that with this new keyword operator. So we set it to size 2, and then we just initialize it with mage and archer, which I'm not going to go over uniform initialization, but you could initialize it like so. Now at this point here, we just are looping through that array, and how I did it was I'm using the pointer arithmetic, where we take the pointer, which remember the party is a pointer, so we take that and we just add the I to it, which I explained a little while ago. That will just be 0, and the party is 0 because it refers to the first element. And then as I becomes 1, then we just add that to party, which it just becomes 1, which will go to this element, the archer. And then we use our arrow operator to access the attack method within the object of character. Now, once again, I could have just used the dereferencer way, which was what we see up here, and then use the dot operator rather than the arrow operator. But you can see that this is much cleaner than this. So we just leave that commented out, and we will just use this. Now, next, I take that level pointer, which refers to this level coin memory up here, which is set to 5. And I just want to modify it. So something that we're going over like we did in the first one, stack. So I modify it to a value of number 2. And then we're going to call this level trigger, which just represents this level up function. We're going to pass in each character, which is what we're doing here again. And we're passing in this level pointer, which should just level them up. And I'll go over that function in a second. Actually, I'll go over that function now. So how it looks like is that we're going to print this out here, which we're going to use this method here using the arrow function to get the name, and then say it's leveling up. And then current will get their current level, which we use that getter for get level. And then we use this increase level, passing in the coin. If you look at this function increase level, it accepts an integer and not a pointer. So notice that I had to dereference this pointer because it is a pointer. You can see integer, which is asterisk, makes it a pointer. So I had to dereference it to get the value. So that's what we do here. And it basically increases level. And then we just print this last print here to get the level again. And it'll show it in one nice line that they were leveling up, and their current level was whatever it was, and then their new level will be whatever it will be. The very last thing we do in this example is we just clean up the memory. Now, it doesn't matter once again because we are at the end of the program, so it will get cleaned up regardless by the operating system. But just for clarity, you know, this is how you do it. You use the delete operator. In this case, this is a single object hero. Remember, we created an hero up here, single object. So we delete it like so. Notice right here that party is an array, and what we see right here. So we can't delete it like this. That will cause an issue. We have to delete it like this, which signifies that it's an array that we're freeing up the memory. Okay, so let's just run this really quickly. Okay, we're gonna choose number 5. All right, so the first thing we see is level coin created, which if we go up, we see that that was one of the first things that we printed here. And then the next thing, this is coming from the constructor, warrior has entered the game. Remember, we have these constructors and destructors. So entered the game, and a destructor will say that they left the game. So we see that here. And then the next thing that we see after we allocate this new memory is that we use the attack method. So we see the warrior, which we are referring to the warrior, attack the enemy. And then we have this function pointer for the level up, passing in the hero. So we leveled them up, and we see that their current level was 1, and then they leveled up to 6. The next thing that we see here is mage archer have entered the game, and that is because we construct them right here. so it will call that constructor. And then we see the party members, which is this line here, and then we're gonna attack, and you see that they attack here, so that's shown here. But we also are calling this level up again, so per each member. So mage has attacked enemy, and then mage leveled up. Same thing with the archer and leveled up. And then the very last thing which we're doing is cleaning the memory up. So the destructor is called, and that's what we see for every single one of them, because we clean up the hero, which is the single one, and then we clean up the array, which is holding the archer and mage objects, so those get cleaned up as well, which, remember, coming back up here, is our destructor, so that gets called. Okay, moving on to the last example, which is the real world example. It's going to be a simulation though. We look into our source folder, make sure to click on it. It's the last one, number 6. Let's go over the information tab. So this example is a simulation of a real world example for when a raw pointer should be used. When writing device drivers, firmware, or interacting with embedded systems, raw pointers are the only option because we need direct access to the hardware registers. Smart pointers cannot be used here because hardware registers do not follow. I'll go over this later on, but they don't follow that, which is the resource acquisition is initialization. Memory addresses are fixed, so you must use raw pointers to access them, and low-level systems cannot afford extra overhead from smart pointers safety mechanisms. So in this example, we access a hardware register, which is going to be a simulation, to flip a bit for an LED light, which simulation. Okay, so our libraries that we have here is IO stream. We have this CSD int, which is, because we use this, which is the uint32, stands for unsigned integer 32. And then we have this thread and chrono, and that's used just to create some small delay. Now this is our fake register, which is, like I said, this is a simulation because we're not going to access a real hardware register. And we just set it to 0 for now, which is going to be off. The next thing that we see here is we have this set console color, which is mainly just to make it look good. So the console color would turn yellow when it's on and then turn white when it's off for simulating the light bulb. And we do so in a cross-platform manner. So if you're on Windows, it runs this code, and if you're on Mac or Linux, it runs this code. Moving on to our display LED function. It looks like this. We're just going to print using terrain operator. So depending on this condition, which I'm not going to go over once again, just kind of brushing through this, but depending on this condition, the light will be turned on or it will be turned off. And this is the sleep part, which I told you about, which just creates a small delay. So it's going to create a 1 second delay before it moves on to like the next state, which will be on or off. This next function here is the update LED, which accepts the register and then the value that we're setting it to. So this is where we set it to. Now this looks familiar here. We are dereferencing this register, which is a pointer, to assign the value, which will be this value here. Once we do that, we just call the set console color, and then we will display that LED, passing in that register, which is a pointer, which this accepts as well. And then this will handle displaying it whether it's on or off. Okay, now lastly, looking at our main entry point, which is very, very simple. We have our pointer here, which is going to be the uint32 that we call reg ptr, and we set it to this fake register, which we just get in the memory address where this exists in memory, which is another memory region that I'm not gonna go over because it's just no point right now. So yeah, we just do this, and this volatile here, I'm not gonna go over it because it also goes beyond the scope of pointers of the whole point of this series, but I do leave a comment here which goes over why that is used in this case. So if you want, you're more than welcome to go and check it out. Like I said, the repo will be in the description below. But anyways, we create the pointer like so, which refers to that fake register that we have here. And all we do here is just show the initial state, which should be off because it's 0. And then we just change it. So we call this update LED, passing in that pointer, and change the value to 1, which this is just a hexadecimal. So it sets it to 1, and then out there we'll call this as turn it off. So let's just run it really quick. Okay, so the last one, number 6, and see it's off, turns on, turns off. So I'll run it one more time really quickly. The first state that you'll see is that it is in off position, and then after 1 second it turns on, and after another second then it turns off. See, it's off, on, off. Yeah, so that's pretty simple. But I just wanted to go over a more real world example of when it is necessary to use a raw pointer versus a smart pointer, which we will get to later on in the series. And this is just one of those cases. It's more so when you're dealing with low level programming, anything like that, when you have to directly access hardware registers is what we're doing here, of course, in a simulated way. Okay, so that is it for this video. That goes over basic raw pointers. It's not an exhausted tutorial, but it is a basic overview of how to implement raw pointers in different contexts like the stack, heap, function, and array. In the next video, I'll go over the common pitfalls and exceptions, and then we will continue on to smart pointers. So if you enjoyed this video, please make sure to hit the like button. If you haven't subscribed already, hit the subscribe and hit that bell notification so that way you know when the next video will be dropping. Remember that the link to the repository will be in the description below, so make sure you go ahead and check that out. And I know there's a few of you who can't wait for me to move on to another tutorial. Don't worry, I have a lot that is coming out. I just want to get this mini series out the way before I move on to other tutorials, whether they're advanced stuff or simple beginner stuff. But I will be getting back to more project-based tutorials very soon, so don't worry. So that is it for now. My name is Ghost, and I will see you in the next video.